Hey everyone, welcome back, and today let's solve Leetcode problem 2661 titled First Completely Painted Row or Column. So we're given a zero-indexed integer array and an m by n integer matrix called mat. Array and mat both contain all the integers in the range from 1 up until exactly m times n. All right? So we need to simply go through each index I in the array, starting from index 0, and paint the cell in the matrix mat containing that integer array at index I. And effectively, we simply have to return the smallest index I, at which either a row or a column will be completely painted in matrix. Keep in mind that index I that we're going to be checking will be in the input array. So in example 1, to better put this into context here, we also are given three images, basically showing the transition of the painting of different cells based on our array. So in this case, our input array is 1, 3, 4, 2, and our matrix is 1, 4, and then 2, 3. For the rows values that we have, keep in mind they're all in the range from 1 to 4, right? Because this is a 2 by 2 matrix, and so m by n would be 2 by 2, which is simply 4. In this case, our output is 2. Well, why is that? Well, they actually give us the moves in order in these images, right? And at the end of the third move, or rather, sorry, the second move, both the first row and the second column of the matrix would become fully painted at array at index 2. That would be the smallest index I, where either a row or a column would be completely painted in the matrix. In this case, that would be the third move. Right? And let's go ahead and take a look at why that is. In the very first move, we see that array at index 0 is 1. And so we're going to paint the cell value that has a 1 next to it. Then we go to the 3. All right, well, we see that 3 is down here, and so we'll paint that cell to be painted as well. So now we have 1 and 3 painted after exactly 2 moves. Well, these are simply just diagonally connected. We haven't actually painted any full row or full column just yet. So let's move on to the next row. We see that we have a 4. Okay, we'll paint the 4 cell, and now as you can see, not only do we have a row that's painted, we also have a full column that's painted. So we fit the criteria of having either a row or a column. We don't need both to be painted at that index I that's minimized. We only need either one of them to be fully painted, either a full row or a full column. In this example, it is both that are fully painted. And so we would return the index 2 because that is the smallest index I, or the very first time that we actually painted either or and a full row and a full column. In example 2, we have our input array to be a lot larger, meaning we have a lot more cells to actually potentially paint, and our matrix is also coincidentally a lot larger as well. In this case, it's going from a 2 by 2 to a 3 by 3 matrix, right? That would really mean that it has 3 by 3 or 9 squares in it as its kind of area, if you will, and as well as that, we also do know that all of the integers or cell values in this matrix are going to be in the range from 1 to 3 times 3. In other words, from 1 to 9. So in this case, we see that our array is going to be 2, 8, 7, 4, 1, 3, 5, 6, 9. This is the order of the number of cells that we have to paint in order. In this case, we paint the 2 first, then we go to the 8, then we go to the 7, then we go to the 4, and then once we actually paint that cell 4 on the fourth move, we'd see that this full column would actually be fully painted by the end of that move after we paint the cell 4, and so we'd return the index I that we get that to be. That would be the fourth move, and the second column in the matrix would become fully painted once we paint that cell 4. In other words, once we paint that array at index 3 cell value. Right, and keep in mind, we could also do this later on in future moves as we actually paint different cells in the array, but we want to minimize our index I or get the smallest index I as a return value, and so to do that, we want the very first time that we have a fully painted row or column, right? So for the constraints here, we see that m and n are the number of rows and columns in our input matrix respectively, and we see that the length of the array is of course going to be exactly m by n, the number of cells that we actually have to paint. And we see that the dimensions of the input matrix, m and n, are both not going to exceed 10 to the 5th power, along with m times n as well. And we see that array I and matrix at any row and column RC, they're not going to be greater than m times n, and they're always going to be at least 1 or higher. So we're also given that all of the integers of the array are unique, and all of the integers of matrix are unique as well. Kind of just telling us that we're always going to have valid inputs, and we don't have to worry about any weird edge cases where we have invalid numbers or numbers out of the range from 1 to n by n. So with the problem statement constraints and examples out of the way, I will give you guys a few seconds to kind of just go over this problem in your head and think of a valid solution, and then I'll show you guys how I would optimally solve this problem in a few seconds. Okay, so what is one very key observation that we can really make here to help us solve this problem efficiently and even lead to our most efficient solution? Well, that really is that the order of the numbers in the array, it actually matters, right? And the reason why is because each number is going to correspond to a specific cell in the matrix, because all of these cell values in the matrix are going to be in that range from 1 to n by n, and they're all always going to be unique, both for the array and both for the input matrix as well, right? So we know each number is going to correspond to a specific individual cell in that matrix. And so because of that knowledge, we basically need to track when all of the cells in a particular row or a particular column, if they are actually painted, right? And once that actually happens for the first time, we know we can immediately return the index of the row or the column, whichever one it really is. So to kind of help us to kind of explain how that helps us lead to our overall solution, basically, first of all, we're going to need two counters. We're going to have a row count to track how many cells are painted in each row, and also a column count to track how many cells are painted, you guessed it, in each column. And basically, we're going to use a dictionary to map each number in the array to its corresponding cell in the matrix, also for a quick lookup, because hash sets and hash maps have big O of 1 or a constant time lookup time. And as we actually iterate through the array, we're going to update the counters and actually check if any of the row or column cells are actually completely painted at each iteration, if you will, right? So with that high level rundown of the solution out of the way, let's go ahead and dive straight into the code here. So what I'm going to do, like I talked about before, is actually initialize my num to position dictionary, or hash map, if you will. So I'm literally just going to call it num to position. Feel free to call it any other name. I think that's how you spell position. Okay, yeah, that should be right. And it's going to be initialized to an empty hash map in Python. Those are just two curly brackets, right? Really, what this num to position hash map is really doing, basically it's going to map each number in the matrix to its row and column indices, right? And that's going to allow us to quickly look up the position of any number in big O of 1 or constant time. So now let's actually loop through the input matrix using nested loops, because of course this is a 2D integer array. That's how a matrix is defined to be, at least in computer science. So for I in the range of the length of mat is what I'll call it, because of course that's the input parameter name, basically standing for matrix. And for j in the range of the length of matrix at index 0, so mat at index 0, the number of columns and the number of rows in the outer loop here, right? So typically I would have rows and columns as my parameters, storing rows and the columns integer variables to be the length of the matrix and the length of matrix at index 0. In this case, I didn't do that. I just directly implemented those two variables in the for loops here. That really is because we're not going to use them too much, and so I didn't want to use an extra integer variables just for that, just because I'm really too lazy, but don't worry about that. Basically, at every single iteration of these nested for loops here, we want to set num to position at index mat at ij, because keep in mind every single cell is going to be mapped to a specific cell value to be that actual value or coordinate ij. So I'll just set it equal to a tuple, right? So very simple here. We're really just populating the num to position matrix, right? We're going to use that nested loop to iterate through every single cell in the matrix here. And really the main observation to kind of take away from this nested loop iteration here is basically here we're simply pre-computing the positions in this num to position hash map, right? That's going to make sure that our main logic is actually going to run very efficiently later. It's going to reduce the need for repeated searches, right? We're literally storing every single cell with every single value in the range from 1 to n by n in these nested loops here in the matrix to be those corresponding values in that number to position hash map. That's literally why we called it num to position. We're mapping each number in the matrix to its row and column indices. right? In the input matrix. Okay, so once we've actually populated and mapped the corresponding values and key value pairs in the num2 position hash map, now let's actually initialize the counters for the rows and columns. So I'm going to call them row and column count, as you may have imagined. And row count is simply going to be a list of zeros, and it's going to have a dimension of the length of the matrix. Because keep in mind, that's basically the number of rows we have. Oops. And very similarly here, I think should be fine. Okay, and very similarly here, I'm going to get the column count. It's still going to be all zeros, but in this case, instead of being multiplied by the length of the matrix, it's going to be multiplied by the length of the matrix in index 0, the number of columns we have in the input. So it's going to be 0 times the number of columns, and the row count is going to be 0 times the number of rows. And again, to kind of reiterate what they're going to do, basically these two integers, or I should say integer data structures or lists, they're going to store the count of the painted cells for every single row and column, where initially we initialize all the counts to be 0, because of course we haven't painted any cells just yet. We haven't iterated through our array just yet. And that goes to my next point. Now let's actually iterate through the input array to actually paint the cells and check for which rows or columns are actually completed. So basically very standard for loop here. For every single index and number in the enumerate of the array input array, right? Enumerate simply keeps track of the current value along with its specific index, right? So basically for every single index and number in the input array, basically for each number in the array, we're finding its position in the matrix and updating the corresponding row and column counts in the row and column count data structures, right? And the variable index, again, keep in mind, our initial iterator is going to literally keep track or store the position or index of the current number in the array, right? So for every single iteration in this for loop here, we're going to get the row and the column value to literally just be num2 position at num. That is the whole point of using that num2 position hash map to get every single cell's row and column value, right? We're literally getting the row and column of the current number and retrieving it via this num2 position hash map, which we got in these two nested loops here. Okay, so once we actually get the row and column values, we want to increment or update our row and column counts at that specific index accordingly. So I'm going to say row count at that index row is going to be basically incremented by 1, and the same thing for the specific column. Increment that by 1 as well, right? We're literally incrementing the count, or the number of times we've actually encountered that, for the specific row and column, which basically simulates painting that specific cell in the input matrix, right? We're simply storing that as painted, okay? So now that we've actually updated the counters, now we want to actually check if the row or column, if it's actually completely painted. And the way we can do that here is simply using a conditional if row count at that specific row, if that's equal to the length of the matrix, so I'll just call it mat, at that specific index 0, or column, or actually I think it's called, column count at index column, if that's equal to the length of the matrix or the number of rows, we know we can immediately return the specific index we're at. And the reason why we can do that is because, again, we're literally simply just checking, well, is the current row and column, is it actually completely painted? Is the current row or the column that we're at, is it actually fully painted, right? This is the main check of the solution here. If row is equal to the number of columns, or column count at the current column is equal to the number of rows, right? We're literally checking if the count of the painted cells in the current row equals the number of columns, or vice versa, if the count of the painted cells in the current column, if that equals the number of rows. If that's the case, if either one of those conditions hold true, using that OR keyword here in Python, we know that basically we've actually followed this instruction, right? We know that the row or the column, whatever is actually true, it's completely painted, and we can return the current index, right? But if we never return the index in this for loop here, we go without actually finding any specific thing, we're going to return -1, right? Typically, this line for this problem, it actually should never be reached based on the problem constraints, because we're always given that the input array is going to be the length of the input matrix. It's going to have m by n cells, meaning eventually at some iteration, we're always guaranteed to paint all the cells and get to a fully painted row or column eventually. But in this case, just for best practice, if no row or column is actually completely painted, once the for loop is actually done executing, we have to return -1 as a fallback. But again, because the problem statement says that the array is always going to be the length of the input matrix, it guarantees that that's never going to happen. So technically, we're never going to return -1. I don't need to have it, but I'm just going to have it for best practice of solution structure. So as you can see, if I were to submit this would actually be accepted, and this should be a valid solution. Okay, looks like I forgot to... Probably made some weird syntax error here. Let's go ahead and check what I did. At mat ij is equal to ij. Seems about right. Let me just kind of retype that. Okay. Row count is equal to 0. Mat, column count. Yeah, feel free to just skip through this part, guys. This is just me updating my very buggy code. Row and column. Increment that by 1. Okay, sorry about that, guys. This should actually be column count, because of course we want to increment the column count for the current column by 1, simulating painting that specific cell in that specific column. Of course, we don't want to paint the row count twice. We want to paint each the row and the column count exactly once for this specific cell. That was my bad. But now this should be accepted, and this should be a valid solution. And as you can see, this is actually really just about as efficient as you can really get it to be. So to kind of reiterate how we're actually kind of using this code as a whole, effectively, we're first building a mapping of the numbers to their corresponding positions or cell indices in the matrix using that num to position dictionary or hash map, if you will. And after that for loop is actually done executing, I should say, then we initialize the row and column counters in row and column count to actually track the painted cells. And as we actually go through the cell and iterate over the array, we're actually going to update the counters and check for any row or column being fully painted as we actually simulate painting each cell at each iteration. And as soon as that happens, we can immediately return the index of the current number in the array. Because of course, that's exactly what we want to try to minimize. We want to return the smallest index I at which either a row or a column will be completely painted in the input matrix. Okay, so for the time and space complexities here, so basically building the num to position dictionary, that's going to involve iterating through every single cell in the matrix, which would be a big O of m times n solution, where m would be the number of rows and m would be the number of columns. And to actually iterate through the array, the other input, well, for each number in the array, we'd have to perform a constant time operation, like the dictionary lookups and the updating for the counters. And so that would be a big O of k solution, where k would be the length of the array specifically. And so the overall time complexity would be a big O of m times n plus k runtime. And for the memory or space complexity, well, for the num to position dictionary to actually build and populate that would store a mapping of all m by n elements in the matrix, which would require big O of m by n space. And the row and column count lists for the actual storing would also require additional space proportional to the number of rows and columns in their inputs, which would mean big O of m plus n. So for the overall memory complexity or space complexity, we'd have a big O of m times n plus m plus n complexity. So if you guys enjoyed the solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.